last class we were talking about the Thomson model atom, which was also known as the Plum-Pudding model atom. And after that we went for the Rutherford alpha particle scattering experiment, and his contribution in the field of atomic model was very impressive. But Rutherford has one drawback which we had discussed in the last class, right? Okay, so according to Rutherford, it was like this here. This is a central positive thing, and he concluded that electron revolves around the the center, positive center. Electron revolves around the positive center here. Okay, but there is a general conclusion that whenever a particular kind of object revolves in a very circular way, it accelerates. It accelerates means it increases the speed. So we knew that now this electron, when it increases its speed, it is definitely going to lose some energy in between here. Understand? Okay. So this is what we used to call as energy here. Understand? So this electron, when it is revolved around the positive sphere, it loses its energy, and gradually this is negative by nature and this is positive, and there is a kind of like a force of attraction between these two. So we will see this electron gradually coming close to the center positive and collapsing with that. So which is not at all acceptable generally, because if this kind of situation arises over here, which proves that atom is totally unstable. So now today we are going to talk about the Bohr model atom, and his focus was on the drawback of the Rutherford model atom. Rutherford was unable to explain the collapsing of the electron with the center positive center here. So today we will talk about the Bohr model of atom here. So his full name is Niels Bohr, and he was a Danish scientist. And he discovered this particular model in 1930 here. Is that clear? Now, according to him, I'm going to write here. Okay. So, according to Niels Bohr, he gave a certain kind of postulate, a certain kind of conclusion about the model of atom. According to him, he concluded that the electrons, they are revolving around the nucleus or the center positive in a particular kind of energy level. Okay, so the first postulate here, okay, he discussed about the particular kind of shell or orbit, we say, or when you go to higher level, they also say energy level. Energy level here. Understand? Okay, if you are not able to understand the first point here, then just go once again. According to Niels Bohr, what he concluded is that, first one, the electron, this is the electron here, electron. The electrons are here. The electrons are revolving around the positive sphere in a particular kind of orbit. This particular kind of round circular thing is what he termed it as orbit, or in some cases we used to call this as shell, or in some cases we used to call this as energy level. Is that clear? And this energy level, he named it as K. This is the one here. This as K. And this as L. And this is M. And the next one as N here. Is that clear? So on. It goes on. Is that clear? So this is the energy level, which he named it as K, L, M, and N. Now suppose, imagine if you wanted to, instead of naming K, L, M, and N, if you wanted to write 1, 2, 3, 4, you can also do that by writing N is equal to 1 for the first shell, and N is equal to 2 for the second shell, and N is equal to 3 for the third shell, and N is equal to 4 for the fourth shell. Goes on. This is the first postulate by the Niels Bohr. Is that clear? What he said, this electron, when it is revolving around the central nucleus, it is revolving around in a particular kind of shell. or particular kind of energy level or particular kind of orbit there, which he named it as KLMN, or also as n is equal to 1, 2, 3 and 4. Is that clear? This is the first one. Now, the second postulate, what he concluded, let's try to imagine this is the Sun, and this is the Mercury, and this is Venus, this is Earth. They are revolving around the center Sun in a particular kind of orbit. But did we ever realize that Earth is slowing down or Earth is increasing its pace? We never had any kind of situation there. And let's suppose imagine this is the Earth. Earth revolves around the Sun in a particular kind of orbit without increasing or without decreasing in speed, which is why it takes around like 265 days to complete one revolution there, right? So we never realized that this particular Earth is neither increasing its speed nor decreasing its speed when it is revolving around this particular Sun here. So from that particular kind of analogy, we will try to understand that his second postulate. He said that this electron here, this electron, when it is revolving in a particular kind of shell, it never loses energy. Is that clear? This electron, for example, this is the K shell here, K shell or K orbit or K energy level. If the electron in a K shell revolves in its orbit, it never loses its energy, just like the Earth is revolving around the Sun here. Okay, so I'm going to write here. Okay, so these particular 2 points somehow, what do you call it, explained the drawback, okay, faced by Rutherford. So this 2 point is very important from the perspective of the Niels Bohr model of atom here. Okay, so now let us go for the other postulates given by Niels Bohr. Okay, yeah. Yeah. So I'm going to write here. This is K shell, L, M, M. Okay? So, now the third postulate. What he has said regarding the third postulate, according to Niels Bohr, he said that this shell here, K, L, M, N, these kind of shell here, K, L, M, N, they have their own energy according to their own shell here. For example, this K energy level is having its own energy, whereas L is having its own energy. M and N, they all are having their own different energies. Is that clear? So let's suppose imagine this is electron here and there is an electron here. Now both the electrons, they are present in a different kind of shell or different kind of orbit, different kind of energy level. They are having different, this particular kind of orbit, they are having different energy level. Is that clear? So third postulates that each energy level, they have what? Different energies. Different energies. Okay? Now, let us imagine, okay, if the energy of this orbit and this orbit is different, then we can somehow conclude here, according to Niels Bohr, his fourth postulate is that suppose if this electron is jumping from this to that shell here, or if an electron is jumping from this to that shell here, understand? Jumping from one shell to another shell, then there is an exchange of energy takes place. Understand? Whenever there is an electron jumping from one shell to another shell, or from this shell to that shell, then there is an exchange of energy takes place. Okay? So the fourth postulate is regarding the exchange of energy here. Sorry, this is making too much noise. Exchange of energy. Exchange of energy. It happens when an electron when electron jumps from where? Electron jumps from one shell to another shell, or from this to that shell. From one shell to another. Okay? So now, I hope every one of you have understood something about this points over here, right? Okay, now let us go for the fifth point here, according to Niels Bohr. So according to Niels Bohr, let us try to imagine there is an electron here, electron, electron, electron here. Let us suppose try to imagine in K shell electron, L, M, N, all of these shells are having electron. Now what he concluded from this particular model of atom is that the electron in the outermost shell here. Now out of this K, L, M, N, which one is the outermost shell? You can somehow conclude that this is the outermost shell, that is the N shell. In the N shell you can find one electron here. And M shell you can find electron here, and L shell you can find one electron here, and K shell you can find one electron here. Now, what he concluded is that the electron which is in the outermost shell is having the highest amount of energy. If you try to compare the energy possessed by all these four electrons, this electron is having the highest amount of energy. Is that clear? So this is the fifth postulate here. Okay. Electron in the outermost shell has highest amount of energy. Okay, so this is the gist about the Bohr model of atom, which even nowadays we used to consider this particular model of atom. So this particular model, even though there are like one or two more postulates, but I feel these are the main postulates given by the Niels Bohr model of atom, and I hope you have understood all about the model of atom. So thank you very much, all of you. Okay, hi once again everyone. So in the previous session we did talk about the Bohr model of atom, and he has given his own conclusion based upon the drawback faced by the Rutherford model of atom. So Bohr in 1913, he was a Danish scientist by nature, and in 1913 he gave the Niels Bohr's model of atom, which we even used to consider nowadays. Now, not only that, Bohr, along with in a Bohr-Bury scheme, he has given us a very important concept about the electronic configuration which we use nowadays. And this particular Bohr-Bury scheme is also referred to as octet rule. Octet rule. Okay? So now we should be discussing about this Bohr-Bury scheme. Okay? Because this Bohr-Bury scheme is an attempt from the scientists to explain the arrangement of the electrons and protons within an atom. Okay? So, according to Bohr-Bury scheme, number one here, whenever we are filling the electron in an atom, for example, I'm going to write here. Now, according to Niels Bohr, he named this as K, this is L, this is M, and we can also say this is N here. Okay? K, L, M, N. I'm sorry, this should be capital letter. Okay? Now, according to Bohr-Bury's scheme, the first point what he said was 2m squared. Okay? 2m squared. Now you must be thinking, what is that 2m squared? 2m squared, what he said, whenever you are filling an electron, you have to fill the electron in K, L, M, N on the basis of the formula 2m squared. Now, this number is 2 which he knew. Now, regarding the n here, this n symbolizes the orbit there. For example, K shell here, K, L, M, and N here. K is normally n is equal to 1. This is the 1. First shell here. And this is second shell here, which we also used to write as n is equal to 2. And this is the third shell, which we also use as n is equal to 3, and n as 4, which we also used to write as n is equal to 4 here. Is that clear? Now, according to Bohr-Buick scheme, in the first row, he said that in this orbit, the electron has to be filled on the basis of the formula 2n squared. Now, I'm going to use that formula here, okay? So, let us talk about the K shell here, K. Okay? In K shell, we are going to calculate 2n squared, okay? 2 into this particular n is number 1 here. This is the first shell here. So, we are going to write, instead of writing n, we are going to write 1 here, and along with that, there is a square here. I hope you all have understood now. Instead, this n symbolizes the number of the shell. And since I'm talking about the K shell is the number 1 shell. And that means instead of writing n, I'm going to write 1. So n square, 1 square. So 2 into 1 square is 1. So 2 ones are 2. So they concluded that in the first shell, you can have a maximum of 2 electrons. Okay? In first shell, you can have a maximum of 2 electrons. Beyond that, you cannot do that. Okay? Now let us go for the next one. That is L shell here. L. Now I hope every one of you must be calculating right now, right? L is equal to 2n squared. Again. Okay. I hope you are following me now. L. This L is which number of shell? That is the number 2 here. Number 2 shell. So instead of writing n, I can write 2 here. That is 2 into 2 square. So 2 square, how much is 2 square? Is equal to 4, which is exactly equal to 8 electron here. So in the second shell, you can have a maximum of 8 electron here. Okay? Now this goes on, right? For, let's say, for M shell here, KL, I'm going to write here, M shell here, N. 2n squared is equal to 2 into, M is number 3, 3 here. So I'm going to write 3 square, 3 3s are 9, 3 squared is 9, 9 2s are 18. So that means 18 electron here is equal to 18 electron. Understand? Now if you go for the N shell here, N shell, N. N is how much? Number 4 is equal to 2n squared. 2 into 4 square. 4 4s are 16. 16 2s are, how much is that? 32 electron here. So in the fourth shell, you can have as maximum as 32 electron. Is that clear? This is the first rule which you should be knowing it. What they can do in the first shell, you can have a maximum of 2 electron. Second, 8 electron. Third, 18 electron. Fourth, 32 electron. Is that clear? Okay. Now let us proceed for the second rule here. Okay. Now, according to second rule, what they concluded is that this Bohr-Buick scheme, it might sound a little confusing, but the moment we are going to work on that, then you will be able to understand. What he concluded from this Bohr-Buick scheme is that outermost electron can have a maximum of 8 electrons. Is that clear? What they concluded? Outermost electron, outermost shell. Can accommodate 8 electrons only. Okay? Now, in order to understand this, we will write some electronic configuration here. Okay? Okay. So, first, let us talk about, let's say, a carbon here. Carbon is atomic number 6. And for this, we have to write the configuration. In a first shell, how many electrons? According to Bohr's rule, first shell, you can accommodate only 2 electrons. In second shell, you can accommodate how many electron? Second shell, how many electron we wrote just now? Is it again 8 electron here? But carbon is 6 here. So we have to write, this is 1, 2, 3, 4, 5 and 6. Understand? Still carbon has the possibility to have 4 more electrons here. Okay? Now let us go for neon here. Neon. Understand? Neon is atomic number 10. So how can we write this? You cannot fill beyond 2 because this is the rule itself, 2m square. Now here, 1, 2, 3, 4, 5, 6, 7, 8 here. 10, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Understand? In the second shell, we have 8 electrons here. Now let us try to think about calcium here. Calcium is atomic number 20 here. Okay. Now when you try to write this configuration, then you will be having a clear idea of the, what do you call it, the second postulate of Bob-Urey scheme here. Okay. So I'm going to write a configuration here. Okay. So 20 means you have to write 20 electron here. In the first shell, how many electrons they can accommodate? 2. Second shell, 8, right? 1, 2, 3, 4, 5, 6, 7 and 8. 1, 2, 3, 4, 5, 6, 7, 8. Now this is how much? 8 plus 2 is 10. Again you are going to write 1, 2, 3, 4, 5, 6, 7, 8. Right? 1, 2, 3, 4, 5, 6, 7, 8. Now all of you please listen very carefully here. Calcium is atomic number 20 here. When you sum up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. That means in order to become 20, we have to write 2 more. Understand? So now, I have 2 kind of possibilities here. Either I can write here, I'm going to circle here, 9 and 10. These 2 electrons here. Because according to 2n square formula, in the third shell, when you just write 2n square is, sorry, I will write it. Okay, so in the third shell is number 3. Alright, so we are going to write 2n square is equal to 2 into, instead of writing n, we are going to write 3 square, 3 3s are 9 and 2s are 18. So that means I have a possibility of writing 18 electron here. But I wrote 1, 2, 3, 4, 5, 6, 7, 8. These 2, I'm just skipping it for the time being here. Okay? These 2, I'm skipping it for the time being here. Now, there are a total of 18 electrons. But for calcium, there are 20 electrons. So, now you must be thinking that this third shell has a possibility of accommodating 18 electrons here. So, you must be thinking, okay, I can write here, write something like this, right? 9, 10. But according to this rule here, the outermost shell can accommodate 8 electrons maximum. So if you think 1, 2, 3, which one is the outermost shell? This is naturally the outermost shell, right? So this outermost shell, it doesn't matter whether it can accommodate 18 electrons or whatever it may be, but the second rule says that the outermost shell can accommodate only 8 electrons here. So we cannot write this 2 here. Is that clear? So we have to write again one shell outside, and we have to write 1 electron, 2 electron outside. Is that clear? The same thing goes for the potassium also. Potassium is atomic number 19. Is that clear? So I can write 1, 2, 1, 2, 3, 4, 7, 8. 5, 6, 8. Now, if you calculate, if you count the number of electrons in that, is 18 here. Now, in order to make 8 one more, I cannot do that. Because if I do that, I am not considering the second rule. According to this second rule, the outermost shell can have a maximum of 8 electron. So, but if I write one more electron, then this becomes 9. So this rule is not what you call is not valid here. Is that clear? So in order to make this more what you call legitimate, what we are going to do, we are not going to write this electron here, and we are going to write one more shell outside, and we are going to write this over here. Is that clear? So for the time being, I guess you don't have to worry about the potassium and calcium, because when you go to class 9, 11 and 12, you will come across a certain kind of principle called Aufbau principle, where you have much better idea regarding the filling of the electrons, right? Okay, so these are the two postulates given by Bohr-Bury scheme, and the third one is very simple. Which I also used to write stepwise. What they concluded is that whenever you are filling the electron has to be filled in stepwise order. You cannot fill the electron that I'm going to write from here, so I'm writing from here. Not something like that. You have to, stepwise manner. Is that clear? So this is the Bohr-Bury scheme, which concluded that each energy level or each shell, they have the possibility of accommodating electron. This electron has to be filled on the rule of 2m square. And the second one is the outermost shell can accommodate only 8 electron. And the third one is whenever you are filling electron, you have to fill in order or in stepwise manner. So I shall see every one of you in the next class. Thank you very much, everyone. Good morning, dear students. So in the last session we were talking about the structure of the model of atom given by Niels Bohr. Now today in this session we are going to move forward with another topic of valency and valence electron. And I guess I had given you a concept of valency in the previous chapter, that is atom and molecules. But today I will go once again on valency and valence electron, and I hope you will listen very carefully. Okay, so yesterday when we studied the Bohr model of atom, we came across a certain kind of atomic model like this. And also according to Bohr-Bury scheme, there were outermost shell could have maximum of 8 electron here. So let us suppose imagine, okay, we take an example of let's say oxygen here. Oxygen is atomic number 8. So atomic number 8 means it should be having how many electrons? 8 here. 1, 2, 3, 4, 5, 6, 7 and 8 here. Now if I tell you how many shells are there in oxygen, how much you're going to say? 1 and 2. Now if I ask you which one is the innermost shell, you are definitely going to say this is the innermost shell. Now this is the nucleus, okay? This is the innermost shell. Which one is the outermost shell? This is the outermost shell. So normally the outermost shell is what we used to call as valence shell. Is that clear? Outermost shell is also referred to as valence shell. And those electrons which are present in the outermost shell is what we used to refer as valence electron. Is that clear? So currently if you just look at oxygen here, 1 and 2, this is the valence shell. In valence shell, how many electrons are there? 1, 2, 3, 4, 5, 6, which is why we used to refer valence electron as 6 in the case of oxygen here. Is that clear? So is that clear? Okay. Now yesterday when we studied the Bohr-Bury scheme, we came to understand according to the second postulate that in the outermost shell there could be a maximum of 8 electrons. Is that clear? Now if you look at oxygen here, how many electrons can you find in the outermost shell? 1, 2, 3, 4, 5, 6 are there. Now in order to become 8, how many electrons is needed? So you can somehow say 1, 2, 3, 4, 5, 6. Now, in order to become oxygen, the second postulate, that is the outermost shell should be having 2 electrons. There, in this case, how many electrons is needed? 2 electron is needed here, which is what we used to call as valency. So valency in this case is 2 here, and I guess I'm not going to go really detailed into that, because if you really wanted to understand the topic of valency, I have done a detailed one in the previous chapter, that is atom and molecules. But when we define valency, we used to write combining capacity of an atom. Combining capacity of an atom here. Is that clear? Okay. So here, now, when we were talking about the Bohr's model atom here yesterday, electron here, and at the center there are proton, neutron, and electron revolving around the proton and neutron. Is that clear? Okay. So now there are some things here that is like atomic number. Atomic number. So in a periodic table we have like 118 elements, and we used to write atomic number, arrange all the elements on the basis of their own atomic number. So normally atomic number is symbolized by letter atomic number is symbolized by letter Z here. Is that clear? Okay. Now here, talking about the atomic number here. Let's say hydrogen is atomic number 1, helium is atomic number 2, and lithium is atomic number 3. Now, what we were thinking about that, atomic number normally is also referred to as the number of proton here. Number of protons. Is that clear? For example, hydrogen is referred to as atomic number 1. Why? Because it has 1 proton. Whereas sodium is referred to as atomic number 11. Why? Because sodium has a number of protons equal to 11 there. Is that clear? But there are 3 subatomic particles, that is proton, neutron, and electron there. Is that clear? So normally we can somehow conclude that in an atom here, look, in an atom here, let us take in the case of sodium here. Sodium has 3 subatomic particles, proton, electron, and neutron. Okay? Okay. Now, sodium is atomic number 11, which is why sodium has how many protons? 11 protons, right? 11 protons. But proton is positively charged, whereas electron is negatively charged here. So it is very important in the case of atomic structure that electron should be having like 11 here. Now you must be thinking, why we are writing why electron should be equal to proton. Electron should be equal to proton. Why? Because electron is negatively charged, whereas proton is positively charged, and they somehow neutralize with each other, which somehow proves that atom is always neutral by nature. So whenever you are like thinking about the proton as the number of protons equal to some values, you should also imagine that the number of electrons should be having the same kind of value as that of the proton. But the number of neutron, since neutron does not carry any kind of charge, so the number of neutron, it matters. Is that clear? This matters. So now let's suppose imagine, okay, this electron here, as I had already mentioned, that this electron is not making any contribution regarding the mass of an atom. Is that clear? So this electron, the mass of this electron is very negligible, that we don't consider that. Is that clear? But if you look at this neutron here, it is not having any kind of charge, but it is having some amount of mass here. So when this proton, the mass of the proton and the mass of the neutron, in this case sodium is 12 here. Is that clear? If the mass of the neutron and the mass, if the number of neutron and the number of proton is 11 and 12, then if you sum up these two, we get the another value called mass number here. Okay? I'm going to write here. Mass number. I guess we have already discussed that in the previous class. Symbolized by the letter A, which is equal to number of proton. plus number of neutron. Is that clear? Number of proton plus number of neutron. This is what we used to call as mass number. Number of proton, it will not change at all. It is always equal to the number of the, it is always equal to the atomic number itself. But the number of neutron keeps on changing. Is that clear? Okay, so with this concept, we are going to move forward with another one. With another topic called isotope here. Isotopes. Okay? Now we understood the concept that whenever we are calculating the mass number, you should always sum up the number of proton and number of neutron. We don't consider the number of electron. Why? Because the electron is having a very negligible mass. Is that clear? Now we calculate the mass of the proton and the mass of neutron. When you sum up these two, you get the value of mass number here. Now I'm going to write it in the case of hydrogen here. Okay, so hydrogen is having proton, electron, neutron. Okay, proton 1, electron 1. Okay, so in the case of what do you call neutron, hydrogen, in some case hydrogen is having a neutron is equal to 0. So here, this is hydrogen here. Whenever we are representing any kind of elements, we always have to write the mass number on top here, mass number on top here, and atomic number down below, like this here. Is that clear? Now I'm going to write here hydrogen here. Hydrogen is atomic number how much? That is the number of proton. How much? 1. Mass number, how much is that? That means number of proton is 1 plus 0 is how much? 1 again. 1. Okay? Is that clear? But there are another kind of hydrogen. There are another different kind of hydrogen where hydrogen is atomic number 1 once again, and they have a neutron 1. Another one, that is 1, 1, 2. Now as you can see, the number of proton is same, number of electron is same. What is changing? That is the number of neutron is changing. So whenever the number of neutron changes, there comes another point, another concept called isotope. Is that clear? For example, now I'm going to, this is for that one here. Now I'm going to write for this one here. Is that clear? So hydrogen, again, atomic number. Atomic number is the number of proton. How much is the number of proton? 1. How much is, this is the mass number on top here. Now how much is the mass number? Mass number is the number of proton plus number of neutron. So how much is the number of proton? That is 1. Number of neutron is how much? 1. 1 plus 1 is 2. Is that clear? Now I shall write for this one here. Hydrogen here. Hydrogen again. Number of proton is 1. I'm sorry. Number of proton is 1. And the mass number is number of proton plus number of neutron. Number of proton plus number of neutron. 2 plus 1 is 3. Now you saw a different kind of hydrogen here. There are like 3 kinds of hydrogen here. 1H1, 2H1, 3H1. Okay? This is also referred to as protium. This is also referred to as deuterium. This is tritium. So in short, you can somehow say all these 3 are hydrogen, but they differ according to their mass number here. For example, in this case 1, this is case 2, in this case this is 3 here. So all those atoms which have the same atomic number, okay, but they have different mass number, is what we used to call as isotopes here. Is that clear? So isotope is all those atoms which are okay. Is that clear? All those isotopes which have same atomic number but they have different mass number. So even in the case of carbon itself, carbon normally is 12 and 6, atomic number 6, and carbon has 6 neutron, 6 proton plus 6 neutron is 12 here. But there are some carbons like carbon 13 also, and there are carbon 14 also. Okay, is that clear? But what is important for you to know is that the chemical property of this carbon, of this one, or this hydrogen, they are somewhat same. Chemical properties of the isotopes are somewhat same. Why do you think so? For example, here, let's say I'm writing carbon here. Okay, carbon is atomic number 6. That means it has 6 electrons. 1, 2, 3, 4, 5, 6. Why I'm saying all these three they are having the same kind of chemical property is that because whether you look at this isotope or this one or that one, all these carbons are having the same number of electrons here. Why? Because the number of proton is 6, 6 and 6. If the number of proton is 6, number of electron is always 6, 6, 6 here. Like here, 1, 2, 3, 4, 5, 6. So normally the chemical property, when we talk about chemical properties, we are concerned with the sharing of the electrons which takes place. So number of the proton and neutron, they are at the center. They doesn't involve in sharing and making the bonds. But who is involved? That is electron. They are involved in sharing and forming the bond, which is why you can somehow conclude that in this case, in this, or in 1, 2, 3, all of this they are having the same number of electrons, and it does not make any kind of difference here. So that is why isotopes are having similar kind of chemical properties here. Is that clear? Okay. So with this, came up with the end of this chapter, that is structure of atom. So I shall be seeing every one of you in the next session. I'll be continuing with another chapter. Thank you very much, all of you.